This is number 18 on that final review packet. So in this one you have a 4 kilogram object attached to a spring, force constant 50 newtons per meter. The mass spring system is placed on a frictionless table. Mass is displaced 20 centimeters and released. So we write down all the information that we have. Mass is 4 kilograms. It says force constant, which we know is spring constant, which is K, or 50 newtons per meter. Then you have delta X, which is 20 centimeters, but centimeters are no good, so we change that to 0.2 meters. So the first part says, what's the time period? Time period is just the period. So the equation for a mass spring system for a period is T equals 2 pi times the square root m over K. So we know the mass and we know the spring constant from the information, so we have everything that we need. So we plug what we know into the equation, 2 pi times the square root of m, which is 4, divided by 50. We ultimately will get 1.777 seconds. So time period of this is 1.77 seconds. Second part is to find the maximum speed. So the first thing to do is to figure out where that maximum speed is located. And anytime you have a maximum speed for this, it's at the equilibrium position. So as it travels through equilibrium, it's going to move the fastest. So when we solve this, we're going to solve it by using conservation of energy, which says that energy initial is equal to the final energy. So initial energy is going to be elastic potential. Final is just going to be kinetic. So we're going to set those two things equal to each other because the elastic potential exists at maximum displacement, which we're given in the problem. And it says it's displaced that 20 and then released. So then it goes from the 20 to equilibrium, which is going to be our translational kinetic energy. Elastic potential energy is 1/2 k delta x squared. Regular kinetic energy is 1/2 mv squared. We can cross out the 1/2 because it has it on both sides. And then from there we know K, and we know delta X, and we know M, so we can plug everything in that we know. So K is going to be your 50, delta X is going to be 0.2, and then mass is going to be 4. So plug in everything that we know. Ultimately, 0.2 squared times 50 becomes 2, and that's equal to 4v squared. So divide 2 by 4 and then take the square root to get a velocity value of 0.707 meters per second. That's the speed that it's moving the fastest, and that's through equilibrium. And now part C is asking for maximum acceleration. So maximum acceleration happens when force is a maximum, so you have to identify where is force a maximum. So the same idea as last time, you want to figure out where the overall quantity is before you can figure out the little pieces. So force is a maximum at maximum displacement because when it's at maximum displacement, it wants to get back to equilibrium. So that's where it has the largest amount of force. So force max is equal to the elastic force because the elastic force is what's going to return it back to the equilibrium position. So F equals ma is going to be equal to K delta X. Now in the equation there's supposed to be a negative. The negative just means that it's going to return back to the original position. So if the object is moving to the right, the force is going to be to the left, vice versa. So plug in what you know, 4 from the mass, 50 for K, and 0.2 for X. So ultimately we get an acceleration of 2.5 meters per second squared. That again is negative because it's opposite the direction of motion. So the negative sign just means that it's going to return it back to equilibrium and it's going to be from the opposite direction of where it's moving.